Hey everyone, welcome back to Real Analysis. The last time we met, we did some fundamental theorems. We proved the power rule for non-negative whole number exponents. But we're going to go a little bit farther with that today. Let's see, we also proved the product rule, I believe. And I don't remember what form of the product rule I showed you, but I think I said first prime times second plus second prime times first. That's what I'm going to be using today anyway. So just a heads up. We'll use this form of the product rule, first prime times second plus second prime times the first, primarily because I don't really remember what form I taught you last time. This is the form I teach in calculus, but most people these days teach a different form. So I'll give you fair warning, this is the version of the product rule that we'll use whenever we need to use the product rule. I'll let you look at that for a couple of seconds more. This is a lemma. It tells us how to compute the derivative of 1 over a function. And it's a lemma because we're only going to use this to prove the quotient rule. After we have the quotient rule, we'll probably use the quotient rule to compute this derivative rather than using the reciprocal rule. So here's our proof. And it involves a trick. But a lot of good math involves tricks. So when we see a good trick, we appreciate it and we incorporate that kind of thinking into our own repertoire. The derivative of 1 is 0. But 1 is g of x times 1 over g of x. So this is just 1. So its derivative is going to be 0. Now, this is also a product. So we're going to get the first prime times the second plus the second prime, and we don't know what that is, times the first. First prime times the second plus the second prime times the first. And remember what it was that we were trying to compute. And maybe I should remember what it was I was trying to compute. Let's see. First prime times second plus second prime, for crying out loud. Come on, you people, when I make a mistake, just say, Dr. Rossi, stop. Is that what you really wanted to do? And I'll say, maybe not. Okay. First prime times second plus second prime, which we don't know, times the first. But this is what we're looking for, and we have it in an equation, so we should be able to solve for it algebraically. We have 0 equals this garbage, g prime of x times 1 over g of x plus the derivative that we're looking for, 1 over g of x times g of x. That's what we got. And we're just going to solve for this thing algebraically. So we'll get these two terms, we'll get this term to the left side. Negative g prime of x over g of x equals derivative of 1 over g of x times g of x. Oh man, this is almost too easy. Look at that for a second, and then we'll continue. This is what we want right here. And all we have to do to get it is divide both sides by g of x. Oh man, this is great. You know, this was so easy. I'll tell you how easy it was. It was so easy, even I could do it. Yep, we just divided both sides by g of x, so we got g of x squared down here. Son of a gun. And that's what we wanted to prove. We wanted to prove that the derivative of 1 over a function is negative the derivative of that function divided by that function squared. Perfect, we got it. Now, I mentioned this is only a lemma typically when we see the derivative of 1 over a function, we're going to use the quotient rule because we know that. The reciprocal rule, the thing that we just proved, is a tool that we're going to use to compute the quotient rule. And typically, since this is a quotient, whenever we see something like this, we'll use the quotient rule. But we use this result right now to prove our next theorem, which is the quotient rule. Now let me make sure I wrote that correctly. F is the top, G is the bottom. So we have top prime times the bottom minus bottom prime times the top all over the bottom squared. Okay, I think I wrote it exactly the way I wanted to write it. And I'll tell you what, pause the video right now and see ooh, goodness, goodness, goodness. I just lost my eraser. No, I didn't, thank goodness. Pause the video right now. Pause the video right now and see if you can prove this using both the product rule and the reciprocal rule that we just proved. Put the video on pause and just take paper and pencil and just work this out. I think you can probably do it in about 5 minutes. So pause and then come back and we'll resume this proof. But I think you can do this, so go ahead and do it. And by the way, after you do this proof, before you return to the video, see if you can go back and also do the reciprocal rule. That's well within your grasp, and the practice will be very beneficial for you. So pause the video and we'll come back in a few minutes. Okay, are we back? And hopefully we did those without too much trouble. Now let me just go ahead and do this in earnest. We write this as a product. And then we use the product rule. And the form of the product rule that I said we'd be using today is first prime times the second plus second prime, and that's negative derivative of the top over the bottom squared. So first prime times the second plus second prime times the first and I guess the first thing I have to do is get a common denominator. We have 2 factors of g of x here and only 1 factor of g of x here. So I'm going to have to multiply top and bottom by g of x. Whoops, whoops, whoops. Did I do something stupid again? Oh my goodness. Do you see where the problem is? Here's first, here's second. We have first prime times second plus second prime times first. This should just be f of x. Please forgive me. Ah, son of a gun, that looks like what we want. First prime times second minus second prime times first, and it's all over g of x squared. So that's exactly what we wanted to get. Okay, we got the quotient rule. Excellent, excellent, excellent. Okay, we got our quotient rule, we got our product rule. We know that the power rule holds for all non-negative exponents, all non-negative whole number exponents. We've already proved this for non-negative integer values of n. So what we need to prove here is that if n is negative, if n is a negative integer, this still works. We'll let k be negative n. If n is negative, then negative n is positive. So k is a positive integer, a natural number. And the significance of this is that the power rule works. For n. Since n is a positive integer, the power rule works. We already know that. Now, we want to show that the power rule is going to work I'm sorry. Oh my goodness, where is my mind? Yeah, n is negative. K is a positive integer. K is a natural number. So we know the power rule works for K. Our goal is to show that the power rule also works for n, given that n is negative. So what are we going to do here? We don't know anything about the power rule and negative exponents. So the first thing that we have to do is rewrite this in terms of a positive exponent. So toward that end, I'm going to write x to the negative k n is equal to negative k. And this is a negative exponent. I still have to rewrite this in terms of a positive exponent to use the power rule. So I'll write this as 1 over x to the k. Now I have x to a positive exponent. Now what? Well, I guess I lied a few minutes ago. Maybe just this once we'll use the reciprocal rule again. And we're going to have negative, the derivative of the bottom, which is k x to the k minus 1, all over the bottom squared. And we can do this. We can say that the derivative of the bottom is kx to the k minus 1 because k is a positive exponent. And we know that the power rule works for positive integer exponents. Okay, now where do we go from here? I guess on the bottom we have the exponents multiplying. So this will be x to the 2k I'll put this k out front. Negative k x. I'm dividing by x to a power, and I have x to a power on top. So the exponents will subtract. K minus 1 minus 2k. So I have k minus 2k is negative k minus 1. Oh, shoot. I forgot my x. Okay. Looking at the exponents, I have k minus 2k, so that's negative k, minus 1. But what is negative k? Negative k is n. So this is n, x, negative k is n, minus 1. So even if n is a negative integer, the power rule works. I'm going to do something a little bit out of order, just for the sake of continuity here. That we look at g of x as being the inner function. We look at f of x as being the outer function. So we have the derivative of the outer evaluated at the inner times the derivative of the inner. And we should also look at a special case So the exponent n is any integer. We have g of x being the inner function and the raising of something to the power n being the outer function. So we have the derivative of the outer function, n times something to the n minus 1. That's the derivative of the outer function, evaluated at the inner function, times derivative of the inner function. This is a special case of the chain rule. And I call it a special case just because it appears to be different than most composite functions. With most composite functions, we have outer to the left and inner to the right, or outer to the left and inner inside. Here we have the inner inside and the outer function to the right. We're going to prove the chain rule, but we're going to wait until after we do the next theorem before we do prove the chain rule. Just for the sake of continuity, we're going to do it this way. So the power rule holds for all rational exponents. That's what we're about to prove. We've proved that the power rule holds for all integer exponents. Our next step is going to be to prove that it holds for all rational exponents. Let's see, we have a hypothesis, don't we? Let the hypothesis be given. Okay, there's our hypothesis. Our first challenge here is going to be for us to write this in terms of things that we already know. Namely, we're going to have to phrase this in the context of a power rule problem where the exponent is a whole number. And here's how we do that. And you know what? That's not how we do it. It might work, but no, I just looked at my notes, and that's not how we're going to do it. Oh, nuts. But we do have to frame this in the context of the derivative of x to a whole number power. Okay, so I'll try this again. Oh, by the way, the advantage of starting here is that we know what this is. We know that this is p x to the p minus 1. Now, I guess somehow I have to get x to the power of p over q here. X to the p over q. Well, I can't just divide this exponent by q. So I'm going to multiply by q. And what this really is, x to the p over q to the q power. Think about it. I have something raised to a power. That whole thing raised to a power. What did the exponents do? They multiply. P over q times q. Cool. But now I have this framed in the context of a function raised to the power of a whole number. And the chain rule comes in. Derivative of the outer So this is derivative of the outer. And I know that that works because the outer function is just something raised to the q power, and q is a whole number. So the derivative of the outer is just the derivative of something raised to the q power, where q is a whole number. It's going to be q times something to the q minus 1. That's the derivative of the outer. Now the chain rule says I have to evaluate that at the inner function. So now I have derivative of the outer, evaluated at the inner, and then the chain rule says I have to follow through by computing the derivative of the inner function. Did I fit all that in? I did. And I might as well say this is what we want. So let's recap what we just did. We started with px to the p minus 1. And it's equal to this pile of junk. So let's write that down. Now, let me make sure I copied it correctly. You know how I am about these things. Okay, I think I have it copied correctly. Not knowing what else to do, I think I'll divide both sides by Q, especially since I want a P over Q in my answer. I have derivative of x to the P over Q here, and we want a P over Q on the other side, so I think I'll divide both sides by Q. And I guess I'll distribute this exponent inside the parentheses. I have something raised to a power, that whole thing raised to a power. So these should multiply. So I'm looking at x P over Q times Q minus 1. And I still have derivative of x to the P over Q here. Okay. Oh, what on earth am I going to get if I distribute that? I'm trying to think of a slick way to do this. X. Let me check my notes. Not much help. So PQ minus P all over Q times derivative of this mess You know what? Q minus P. I have P over Q x to the P minus 1 equals x to the PQ minus P all over Q times the derivative of x to the p over q. That's where we're at. I'm going to divide both sides by this piece of junk, just so that I can isolate the derivative of x to the p over q, because this is what we want. So I'm going to divide both sides of this equation by that piece of junk. So let's see, I'll get x to the pq minus p over q, and that's equal to the derivative of x to the p over q. So now all I got to do is simplify this piece of junk, and hopefully I'll get an outcome that won't embarrass me. So I have derivative of x to the p over q equals this piece of junk. And you know what? I guess I can just put the p over q out front. I don't know why I integrated it with everything else. But x to the p minus 1 over x to the pq minus p over q I have x to 1 power being divided by x to a different power. What happens? In this case, x to 1 power divided by x to another power, don't the exponents subtract? This exponent minus that exponent. So we'll have x to the p minus 1 minus pq minus p over q. Holy moly. I'm going to have to get a common denominator. So we'll have p over q, x, and I get a common denominator here, so this is pq minus q, all over q, minus pq minus p over q. And oh, thank goodness this is what this is working out. Okay. So PQ minus PQ is 0. And then we have negative, and negative P is positive P minus Q. Oh, good. P over Q X. PQ minus PQ is 0. Negative and negative P is positive p minus q. So p minus q over q. We're getting there. P over q x. And I'm going to split this numerator up. I'm going to put each term of the numerator over the denominator separately. So I'll have x to the power of p over q minus q over q. Oh, thank goodness. This is working out exactly the way I want it to work out, and I'm not going to embarrass myself after all. So that's p over q, x to the p over q minus 1, which is exactly what we were supposed to get. So let me just summarize. We started here. The derivative of x to the p over q, where p and q are both integers, q non-zero. Oh, shoot. You know, one of these days I'm going to learn how to write. We have the derivative of x to the p over q, and here's where we end up. P over q, x to the p over q minus 1. So we have proved the power rule for all rational exponents. We are not going to prove it for all real number exponents. There's a lot of heavy theory that goes into that. But we will take it as far as showing the power rule for all rational exponents. We do have one sin to atone for. We have not yet proved the chain rule. In our next video, that's going to be our first order of business. Look over this closely, take notes, hit the pause button, make sure you can justify everything. And when you're not doing math, please exercise good judgment. I want to see all of you as soon as possible back in the classroom, all in good health and all perfectly happy. It will happen. Things are not always going to be like this. So again, don't worry about what we can't do right now. Let's just worry about what we can do. Let's get to work on our studies, and let's exercise sound judgment. And I really am looking forward to seeing all of you.